Okay, so today we are glad to have Dr. Chen from the NREL. So she is our alumni. So she got her PhD back in 2001. So she's the chief scientist at NREL, so NREL Grade Planning and Analysis Center. Before that, she was at MISO for 20 years. So, and her role over there was she played the key roles in the startup and development of MISO energy and ancillary service market. So her research focus is electricity market design, computation, and power system operation. She holds PhD in electrical engineering from Washington State University and MBA from the Indiana University. Dr. Chen is a fellow of the IEEE. And with that, let's give it back to Dr. Chen and ask her to start the presentation. Thank you.
Thank you. Thank you very much for inviting me to this seminar. It's been 22 years. This time goes very fast. Since I graduated from WSU, I remain very grateful for the education I received, especially thanks to my PhD advisor, Dr. Manning, and Dr. Boss, both, who taught us the foundation of understanding power system operations and economics. Today, my presentation will focus on the uncertainty management in market operations. So the ISO and RTOs manage uncertainty across planning, capacity auction, and market operations. So in the long-term planning horizon, in most cases, the members are responsible for the resource expansion and setting the decarbonization goals. ISO RTOs mainly focus on the transmission expansion. And when the resource is ready, and they will actually submit into the generation interconnection queue, and RTOs will perform the study and to ensure the reliability. And then the ISO RTOs also has this resource adequacy construct. Many of them has this capacity market, to have the auction in either 1 year or 3 year forward time frame. And then there's a planning reserve margin established in order to meet the reliability target. So today it's mostly follow the 1 day in 10 year, basically 1 event a day in 10 years. And then there's also capacity accreditation to reflect the resource contribution differences. For example, the renewable wind, like the capacity credit is maybe around 15% at the MISO region, because it's not, even though we have this installed capacity, the wind may not always be able to output at the maximum. In recent years, there's a bigger question on whether the future resource portfolio will have sufficient reliability attributes for operations. When we get into the operational time frame, the process is really an uncertainty and risk management process. So the industry basically adopt this multi-stage commitment process, because some resource will need a long time to start, but in the long lead time, like showing this diagram, MISO process started from 7 days ahead. The uncertainty in that time window is very high. The forecast error can be over 10%, and then so in that process, we don't make the decision for every resource. It's only focused on the resource, like a long lead resource. You really need to decide, to call them or not. And then gradually, this multi-stage will go to day ahead, intraday, and then the real-time dispatch. So this kind of making decision for resource, like really need to take action, and then defer the decision for other faster resource to future process. So that's basically the idea behind the operational process. And then there's also market product like energy operating reserve. It's traditionally operating reserve is to handle the 5 to 10 minutes kind of uncertainty on the imbalance between supply and demand and also some contingency event. But in recent years, with the renewable penetration, there's additional uncertainty from renewable forecasts and other uncertainties. So new products are introduced, like a flexible ramp product and 30-minute or 1-hour product. So looking at the resource adequacy timeframe, right? Traditionally, resource adequacy will only look at the capacity adequacy, basically, just in terms of a megawatt, for the peak load. Normally, it's a summer peak. But with the more kind of extreme weather event and also more weather-dependent resources, the industry start to see the need to address other adequacy, for example, the energy adequacy. So the top graphs show, like during Winter Storm Uri, the wind output is very lower across multiple regions for about 12 days. So if you only look at the megawatt adequacy, you may not be able to have enough resource with this sustained energy, right? Like fuel assurance to cover this long period of low renewable. And then also the bottom graph shows this flexibility need. So the forecast error in day-ahead real time may actually cause a larger ramping need in real time. So you need flexible resource to quickly pick up this kind of ramping needs. And then so in MISO started some recent initiative. So I have a link there basically to look at the essential reliability services like energy adequacy, flexibility adequacy, and the voltage stability issues, and then evaluate whether this current planning process can result in sufficient attribute for future operations. And then certainly there's a big gap between existing planning process and tools, right? And then between the planning and the operations. So the industry start to see the potential inadequacy issue in the long-term resource planning. For example, the MISO, looking at the members' resource planning and the future load growth, we'll start to see the gap, between the two. And for SPP, similarly, the planning reserve margin will significantly reduce, in the next 5-10 years. And then recently, NERC, there's an effort in NERC trying to develop standard on the energy assurance. And then goes back to the operations. There's certainly more complexity in operational uncertainty management. So traditionally, we kind of focus on the MS1, right? All these control room application like EMS, the state estimation, contingency analysis, it's a focus on the MS1, and then also the main uncertainty, come from the low forecast error and this kind of contingency event. But with the new portfolio evolution, first of all, even on the load side, we start to see more behind meter distributed resource that can introduce challenging on the low forecast and the potential high forecast error. And then certainly renewable like wind and solar have additional uncertainty, in the forecast. And then on the generation side, the new generation, the new build are mostly the gas unit, like combined cycle, a more efficient gas resource. there's a certainly dependency on the gas industry and potentially like a fuel assurance problem. Then of course the uncertainty across the things, basically the scheduled interchange, and the last but not least, the biggest uncertainty actually, especially for large region like MISO, is the transmission congestion. So this left graph is basically from some MISO presentation to the board, and then you see like transmission congestion it's marked as a red. So it's a basically the one with the most challenging today. It's very difficult to predict congestion in multi-day or day-ahead time frame. And then the new resource integration, start to see more storage, the DER, basically distributed energy resource, demand response resource, and then even on this traditional resource, the new build of the combined cycle, normally it's multi-configuration. So there's a bigger question on who should optimize what, right? Like storage or DER, you can have a large number of small resource. In recent, like a FERC order, like 841 or 2222, you require the integration of like resource with 0.1 megawatt. So if you have this large number of small resource, it definitely will introduce more computational challenge. And sometimes, if you cannot reach the MIP gap, mixed integer program gap, and then you may not even be able to optimize this resource well. But on the other hand, if participants manage this resource on their side, they also need to predict like for example future price, and there's a lot of uncertainty associated with that. So I think the industry is still to explore how to schedule or manage this resource in the market and the daily operations. And then so I mentioned earlier, this market process, right? The operations actually, the industry figure out this kind of multi-stage process. It's aligned well with like this stochastic stochastic optimization process. Basically, you have this, for example, in the multi-day, 7-day time frame, you include this future resource availability or forecast, but at that time window, you don't make decision for all the resources. You only make decision for the long lead resource and leave all these other resources to the future stages. So that can greatly improve the efficiency. Basically, you can wait until the forecast information is better than to decide whether you truly need to call some fast start resource. This multi-stage process definitely will stay, will still need in the future, when the resource portfolio have a bigger kind of a difference on the characteristics. For example, people are developing this long duration resource, right? Trying to address this multi-day energy adequacy issue. So those kind of resources probably need a multi-day or multi-week type of optimization to determine, when to charge or discharge or procure fuel. And then, then you move to the day ahead, intraday, and then finally the real time. And then this process, of course, at all these stages, there's an uncertainty associated with them. The reserve product introduced to address this gap. For example, MISO in recent years introduced this short-term reserve. It's a 30-minute product, but it was designed to cover 3-hour uncertainty. And then there's a flexible ramp product, really trying to cover between 10-minute and 30-minute uncertainty. And then operating reserve is to, between 0 and 10 minutes. So the first is to be clear about what this reserve product was intended to cover, right? The uncertainty, what the time window we're trying to cover. But then next is to look at the uncertainty within this time window, and then to determine how much reserve we need. It's like just like buying insurance, right? So in certain hours you may have high uncertainty, but other hours it may be lower. So it's prudent to procure this reserve product more dynamically. So these are some recent work in recent years before I left MISO. There's some work between the market operations and the R&D to basically develop a more dynamic reserve process. So what we looked at is basically to quantify the uncertainty across different seasons, different months, different hour, and then to identify the distribution, right, uncertainty distribution, and then define the reserve requirement to cover, the target, the level of coverage, basically, for example, 97 percentile during normal condition, and then 99 percentile during emergency. And then it's defined based on different time, season and different time of the day. So that actually was built into the current MISO operational process. The basically trying to procure reserve more basically targeted towards the system needs. But this process today is still kind of retrospective. Basically look at the, past 3 year or, basically like most times past 3 year, and then the uncertainty distribution pattern. But of course, the portfolio is evolving, so the pattern generated from history may not be a good prediction of future. And also, in recent years, there are a lot of emergency event, and then what operations really need is like if we can predict this type of event and then prepare the reserve or all these emergency actions ahead of time. That's really what they want. But we're not quite there yet. The next thing is really talking about the location. So the system-wide uncertainty definitely, it is increasing. But a lot of the time, the emergency actually happen in a local area. So due to the transmission import export limitation, right? So traditionally, we consider M-1 in the continuity analysis, and then also in the local L1P market, right? We do look at the congestion. It's a security constraint, right? Unit commitment and economic dispatch. But in that formulation, we only look at the energy, right? Basically, to look at the cleared energy, can this energy megawatt be transferred across the transmission system? But it didn't typically look at the reserve, right? So, for example, if in certain region you have import limitation, or if you lost largest generator, right, you won't be able, if you can't import due to transmission constraint, you want to procure enough reserve in that region to cover the loss of the generator. But if we don't explicitly formulate that in the clearing process, you may clear reserve outside of the region, right? Then in the end you found out when you need it, it cannot be transferred into the specific constrained area. So it's actually 10 years ago, this kind of issue happened at MISO. So we kind of introduced this constraint to reflect reserve deployment impact on the congestion. And then by include this constraint, you will be able to push reserve to the right location. And then also, because there's also uncertainty associated with all the forecasts, and the renewables in these different zones and regions. Ideally, we should also develop the dynamic requirement, for this local area. So this part is also some first step trying to define the basically called the largest uncertainty event. It's not just the largest generation event. And based on the aggregated uncertainty, basically say in certain zone, you could have largest uncertainty event in this zone, and then we need to basically schedule reserve, to cover that. Again, this is a very first step. Look at it on a zonal basis, but of course, we know sometimes like the MISO to define zone is not that easy, for such large region. Ideally, in this probably also reserve also need to be considered on a nodal level. So this one is on some research project MISO collaborated under APAI project on stochastic look-ahead commitment. So this is a nice project to basically prototype these kind of future tools. The first is on the data analytics piece to look at uncertainty distribution and generate a scenario. It's on a more like an ongoing basis. For example, when we clear 3-hour look ahead commitment, this actually is running every 15 minutes. We'll be able to generate the scenario prediction, right, for the next 3 hours. And then based on that, we can evaluate, right, under each of these scenario, what's the potential impact. And then finally, there's a stochastic optimization, basically look at all these scenarios to determine the commitment that will be able to cover all these scenarios and with the most economic decision. So this ESIC, the prototype actually was very promising. But of course, there's still a lot of work like upfront, how we can generate robust stochastic scenarios and then fit into the process. And then, of course, the biggest work is also for operations to build trust on that. So next is about the pricing. So when we are talking about market, of course, pricing is one of the key important factor to look at. Basically, the efficient market design need to generate a price, right, for incentive compatibility and also provide the incentive for future resource investment and also, these retirement decisions. At the beginning of the market, MISO and other RTOs put a significant amount of effort on addressing this non-convexity. Basically, OMP market is really generated. There's some noise. Okay, now it's better. Generate this locational marginal price, right? The marginal price may not be able to cover the total cost, like some generator with fixed cost, like startup no load cost. So there was significant effort in trying to address that issue. Sometimes you can call a block loaded generator, it cannot set marginal price, and then when it's only to depress the price, or it's like an offset load. And then there's some great work done, by MISO and other RTOs on the area of convex hull pricing, really trying to incorporate this fixed cost into pricing and to minimize the uplift, basically make whole payment. And then there's some recent work on average incremental cost pricing, aim to eliminate all the make whole payment. But this work will really address the problem nicely when the final solution is actually close to optimal. But the reality is today operator sometimes need to make a lot of out of market action. Like during emergency, they may call just manually call on some resource or deploy some load, emergency load curtailment. When this happen, the market price actually tends to be depressed. And so MAS also did the work like emergency pricing, really trying to basically, if you deploy emergency resources, kind of like shift to the supply curve to the right. And then this emergency pricing mechanism just trying to basically introduce some administrative price for this emergency actions or resources, so that the price is not going to be depressed. So basically, initially it may look like seemingly free, but now you apply some price to this kind of emergency resource, so that in the end the price will not be depressed. And then lastly, we talked about this reserve product, and then how to define the requirement and the demand curve, basically the value of this product. It's also a lot of interesting work around that. Before we can truly get this kind of dispatchable demand, right, for demand themselves to offer, they're willing to pay into the market. That probably would take some time, if for that to happen, before we can truly get the willing to pay from the demand side. So we have to basically define this reserve demand curve to show the reliability value of this reserve product in order to keep the lights on, right, to be able to serve all the load. So that's on the pricing. And then so we talked about all these interesting and challenging problems, right? Next is the opportunities to develop next generation uncertainty management process and tools. So I think last year there was a workshop from National Academy of Engineering, led by Professor Boss and some other NAE members. The report really outlined some of the issues and potential future opportunity, right, to address this issue. Really, the industry is going through rapid portfolio change, and so when we developed all these solutions, or in doing the research, we should not only look at the existing system, I have to also look at the future portfolio. And also it's not the final future, but also along the process, the portfolio can be very diverse or dynamic. Have to be able to cover all these steps during the transition. So really, the reliability standard and tools, traditionally like the N-1, these need to be evolved and to better manage the future portfolio. And then today we're still missing this resiliency standard, how to handle the extreme event, what's the target, how much the society is willing to pay, right? And then this standard need to be developed. And then also on the market design and tools, the goal of the market is really trying to maximize social welfare, but the new under the new kind of world, we need to achieve that goal while we having this high uncertainty and variabilities. And then we need to generate the signal, for the results to basically follow the market dispatch and all these decisions, and then also making prudent investment or retirement decision based on the market signal, and facilitate non-discriminatory market participation for all resource types. So like I just put together a few slides looking at the existing reliability standard, right? For example, the BAO 001 real power balance control performance, and then we have this AGC system and regulating reserve. It's all kind of built around that. And then the BAO 02 on disturbance control standard, the industry basically introduced the continuous reserve to address the G-1. And then, but today there's a new risk, besides this 0 to 10 minutes or 0 to 15 minutes kind of uncertainty. This additional uncertainty, and also extreme event with a very long tail distribution, how to address this. And then also traditionally reserve product was defined on a megawatt basis, right? It really didn't specify how long it need to last. And but with in some area, we already observe a larger amount of the reserve cleared on the storage device, and then you have to look at this megawatt hour, how long, both in terms of energy and also reserve. And then on the resource adequacy, planning, the industry basically adopt this 1 day in turn. So we discussed early, whether that is still a good matrix, right? Especially for the energy adequacy need. Some areas start to discuss about using expected unserved energy. And also a bigger question is the current planning tools may not be able to reflect the operational constraint. Are we still good basically just wait until the operational time frame to address this operational issue? So on the transmission side, I think, like I mentioned earlier, that probably is a even bigger gap. Today we do have the EMS application, or also, in both planning and operations, we run N-1. But, in the future, this uncertainty scenario, like loss of the weather-dependent resource, the size could be much larger than N-1. And then, we talked about the reserve, right? You have to procure that at the right location because of the transmission congestion issues. And then in the future, there's a DER, on the distribution level. A lot of these are on the distribution level. The grid operator may not even have visibility. And then as a coordination between transmission and distribution. The congestion forecast, especially in the multi-day or day-ahead time window, is still very challenging problem. Then next, the voltage issues. Today is not addressed very well, even in today's system. There's very limited capability to evaluate the voltage stability issue in operations. Mostly it's on some offline process. And then in the future, with this penetration of inverter-based resource, I feel like there's a huge gap to be addressed. So, the last few slides are basically just summarizing 4 different areas. The first is on the risk management. But first of all, we need tools and of course the research to develop better tools for probabilistic forecast. Today most operations still use deterministic single point forecast, but operations definitely they need to evaluate more scenarios, with this probabilistic forecast and generate a meaningful scenario. These are built upon the data and analytics and machine learning approaches. And then after we quantify this uncertainty, the next question is, we really need to have a target, basically how much uncertainty or risk we need to cover. So that basically goes back to the reliability and the resiliency policy. Really, if we define a target, I think operations will just treat that as a hard constraint. They will try everything, to meet that target. But otherwise, it's pretty difficult for control room operators to take decision, during this kind of extreme situation. And then in terms of the market construct, right? Currently, the capacity market is 1 year or 3 year forward, but the portfolio can evolve very fast. Beyond that, for example, the member long-term resource planning, it may have some embedded missing element, but right now there's no good kind of signal or process to quantify the portfolio need. So, you know, how to address this long-term resource planning need. You know, we need better tools and process. And then now when you get into operational time frame, for example, I'm also drawing 7-day unit commitment, but that's just a kind of not a market construct, right? And then it's only for a small number of long lead units. And then in the future, if we have this long duration storage and then also maybe some fuel assurance need, you know, whether this multi-day market, you know, is needed. I think in some area there's a discussion, you know, on that specific time window. And then in the intraday, it's kind of similar problem. You know, today we run unit commitment, but there's no price signal. You know, in some instance, when, for example, RTO declare emergency, operators, they may know the transactions may come from outside, but they don't know how much, you know, what's the quantity. And then, so they have to also still take their own action. But you may find out sometimes the market may, or the outside may overreact to that signal and then introduce some inefficiency. So the intraday market is also an interesting area to look at. And also that may also help on, for example, the short duration storage scheduling. And then also the clearing mechanism, you know, whether it's through the stochastic robust optimization or maybe, you know, through the introduction of market product. And then when we introduce this market product, we have to also look at the location, right? Make sure that they're procured and can be delivered through the transmission system. The second area is on the reliability attribute. So we talked earlier how we can ensure the attributes in future portfolio. Basically, the first part is on the risk quantification, uncertainty, you know, quantification, and then how we're going to kind of address this uncertainty, right? A certain reliability attribute is required for operations. You know, can we just wait until operations to address that? And or should we also make sure, you know, in this future portfolio, we'll have enough resource to be able to provide that. And then also for this low probability, high impact risk, it may require, you know, high cost to procure enough of this attribute. You know, how can we justify? And then again, it goes back to the standard. And then yeah, so what time frame to look at this attribute? Is operations only, or maybe capacity market, or even long-term resource planning? So the price signal. So today, you know, we have this L1P market. It works really effectively in both the you know, the economic kind of commitment dispatch as well as the congestion management. But in future, in both, like in location, we talked about, it's probably not just energy, but also when we procure reserve, we need to look at location. But when we have the DER or demand response, it makes sense to aggregate this resource to create something like a virtual power plant. But if we aggregate them across multiple locations, kind of, you know, kind of a conflict with this locational concept, right? So how to address that? You know, there's actually haven't figured out a good solution for that problem. And then the marginal side, you know, we kind of discussed earlier for the generation side. There's some kind of fixed costs. You know, there extensive work to address that. But in the future, when with large renewable penetration, you know, we'll have probably reduced of this fixed cost, and then the marginal cost will be close, you know, to zero. Then how the market can still send the right price and incentivize the response, right? And then a key related issue is how to incentivize this demand side participation, and then for demand side provider willing to pay into the market, and there's coordination across different market, like between capacity and the energy ancillary service market, and which part should take care of what, and then also the market to market, between different the market, like for example PGM or MISO or SPP across themes. There are a lot of issues need to be addressed to improve the efficiency, and then in the future there's a T&D coordination along basically between the wholesale and the retail side. The last, I think this is the last slide, is on the new resource integration. We discussed earlier about who should optimize what, the trade-off between optimality and the complexity. And then the resource side, especially if we have the aggregated resource with storage, the participant side need to manage their own uncertainty. So in terms of both the quantity and the duration, there will be uncertainty associated with this future new resource. How can we basically need to somehow consider that when we schedule on the grid side, right? Because this new resource will look very differently from traditional resource, and there's a question in terms of whether we need to do centralized or distributed market clearing, especially with more distributing side participation. And then this new flow control device, like NREL is doing this NTP national transmission study. There's a indicate the benefit for this HVDC, like interregional HVDC. This flow control device, how we can maximize the value in terms of addressing congestion and transfer efficient resource across region. So I think these are the other basically 4 areas. I feel like there's great opportunity for future research, but those are definitely some very challenging problems, and so for the next generation of researchers to address, and to have a smooth transition to near zero future. With that, it ends my presentation. I'm happy to take any questions.
Okay, let's maybe take question from the audience and the team. So anybody online want to have question from our speaker? No, nobody online. Okay, so then you guys, you may have questions.
Yeah. So given the increased uncertainty and contingency plans, like you said, N-1 is no longer really sufficient for future planning, and kind of the lessons we can take away from, say, Texas, when you rely entirely on market forces to do your resiliency, it falls apart as soon as you hit contingencies that you haven't considered before. Given all that, do you see market forces alone as being sufficient for this kind of planning, or do we need to look elsewhere besides just financial incentives to, say, more broad or even more vague regulation allowing for adaptation to contingencies that maybe we didn't plan for but are in front of us?
Yeah, so that's a great question. The market design and all these kind of planning is building around basically what the scenario or what the system condition, right? You anticipate, but like this extreme event, normally, especially we see these kind of new events more and more, right? It's probably not even reflected in the history. It's pretty difficult to predict. So they are researching in this area, trying to build a future climate model, and then to be able to generate better these kind of extreme scenarios, right? So first of all, that part still need a significant development. The second is like, even if we can see this event, right? How should we address that? And then, so if it's a low probability and high impact, right? Because the probability is so low, and even if the impact is high, sometimes it's hard for the individual company or participant to kind of justify the investment. So I actually read some article basically discuss this kind of situation. So in this kind of situation, the policy side probably need to step in. Basically, for example, even today, like the N-1, right? The loss of largest generator, the probability actually is pretty low. So, but because there's a standard saying we need to cover that. So all this planning and operational process basically are designed to cover that. And I looked at one as like a MISO contingency reserve requirement that can cover 99.9 some % of the generation outage risk. But in the future, definitely in order to cover that level of risk, right, the aggregated risk is going to be very costly. So we do need a standard, I think, basically how much the society is willing to pay, and then the policy side to define a standard. So another way is probably basically for the demand side, right? They can, if there's a the construct to basically for the demand side to share they're willing to pay, right? Then in the end, we may plan on and construct the market and operate in a way to take into consideration, right? In the end, if certain results they are not willing to pay, then in this situation they will be curtailed first.
Okay, thank you.
Thank you. Other question?
I have a question. So for the generation of scenarios, how are you generating those scenarios? And after generating the large amount of scenarios, how did you reduce those scenarios by using the clustering algorithm that you just described in the slide?
Yeah, so there, there's a paper, in the reference, there's another paper about the scenario generation and scenario reduction. It's definitely right. The operations normally cannot look at that many scenarios, and this scenario reduction technique basically look at the reduction and to minimize the error it introduced. Some type of like clustering at a different kind of probabilistic region.
Thank you. And the second question is, so to solve that large scale stochastic optimization problem, you showed that you solved that problem within 2 to 3 minutes. So did you use any kind of decomposition techniques to solve that problem?
Yeah, that one was the eGrid tools developed by initially Sandia National Lab, but right now it's also used in different labs. That was using progressive hedging. It is like basically solve different scenario and then trying to get agreement on the final unit commitment solution. It's like when you solve this individual kind of scenario, you can basically parallelize and then go to the high level to do the kind of arrange the solution to get agreement, then to the next iteration.
Okay, thank you.
Mm-hmm.
Yeah. You mentioned about storage participation in intraday market. Can storage come as day-ahead market as well to support the loads for the future scheduling?
Yeah. I mean, definitely in the forward process, we definitely also ideally need to consider the storage optimization, but the problem is today, in order to optimize the storage device, it will introduce a lot of computational challenge. So in most of RTOs, the storage actually is not optimized in the commitment and dispatch process. The commitment definitely is a computational issue. The dispatch side, the issue is more like the clearing window is not long enough, right? In order to kind of schedule a 4-hour storage, you need to look, beyond 4 hours or even 8 hours in order to schedule it well. And then, but today, these are not kind of considered well in the commitment clearing process.
Thank you.
Anjan, you have a question, Anjan? I think you are muted. So.
Yeah.
Yeah.
Oh.
Yonghong, all of these presentations, whenever I sit in on them, that gets very complex, because you have markets, you have operational procedures, and everything else. That makes it very, very difficult to figure out where the problem lies. So let me ask a very simple question that Mani and I have been discussing recently with SPP. In the planning process, what needs to change from the way we are doing planning today to make sure that you have enough generation and transmission 5 years from now? You see, what I'm referring to is that every year NERC comes out and says this summer the chances of the probability of losing power or having to shed load gets higher. Every year it's getting higher. So we're doing something wrong in our planning, right? So the question is, what needs to change? And you kind of hinted at some of it here by saying that, if you can put some of these uncertainties in the calculations, then can we? So one of the things we hear, and SPP kind of also said they're doing some of it, is, and you probably know more about what other RTOs are doing in terms of running production costing models, right? For with different using Monte Carlo, right? And so that seems to be a reasonable thing to do. The question, and you're right that NERC hasn't come out and said what the standard should be for that. But is it your feeling? I ask two questions. Is it your feeling that that's one process that might work for planning? And the other question is, if you have run some of these kind of things, let's say at MISO, our back of the envelope calculations are saying that if the uncertainty increases, your need for energy, megawatt hours, increases very fast. That is, it's exponential. So those are the two questions.
Yeah, I think definitely you're right. The planning process currently, it doesn't capture a lot of the operational uncertainty, right? So they may also do Monte Carlo simulation, but most of the time it doesn't consider the intertemporal constraint or like a unit commitment constraints, right? And then just even ramp constraints not considered, it just assume resource can ramp very fast. And but if you have that California, that kind of duck curve, in the end, you may not have enough ramping capability, right? And then, so like introduce this production cost model, trying to formulate some of the resource constraint, that can definitely address this variability issue. But operations also have another issue on uncertainty. Now, even today, for example, the MISO, we normally don't see any issue in day ahead. If that day ahead, if you have perfect foresight, right, you can commit unit ahead of time, to basically some slow start unit, you commit them and let them ramp ahead of time. That will address the issue. But when you get into real time, the problem is a significant amount of the resource will not be able to start. So they pass their startup notification time. So you only have a small subset of resource can respond. And then when you get into this high intra-hour, uncertainty or forecast error, then you may not have enough ramping capability, right? So we kind of look at how these can be introduced in the planning stage. It's probably unrealistic to look at multi-stage, right? And we don't even have a good data, data set to reflect the operational uncertainty distribution. And so planning stage, they may use some kind of reserve requirement, trying to capture that. But I think there's a bigger question in terms of how do you define that well to address, to really reflect the operational need.
Thank you. Yeah.
Yeah, thank you. Is there any more questions online? Or I saw the one hands up, so was it? No, there's nothing. Okay. So with that, we really appreciate Dr. Chen for giving us that excellent talk. So we really appreciate for your time. So, and with that, let's take.
Thank you. Thank you very much.
Thank you. Okay. Have a great day.